Here's a parallelogram, and a reminder that the definition of a parallelogram is a quadrilateral in which both pairs of opposite sides are parallel. In this lesson, we're going to look at different ways to prove that a quadrilateral is a parallelogram. We'll start with being given a quadrilateral with opposite sides parallel. And of course, that's the reverse of the definition. And all definitions are reversible. Here's another one. We're not given that the opposite sides are parallel, but we are given that it's a quadrilateral with both pairs of opposite sides congruent. So we draw one of the diagonals, and we see that we have two triangles that are congruent by side, 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 with one of the sides being a shared side congruent to itself, which is the diagonal DB. And because those two triangles are congruent, we can mark three pairs of angles congruent because they're corresponding parts of congruent triangles. And the pair of angles labeled with a green arc are alternate interior angles relative to the top and the bottom. So the top and the bottom sides of this quadrilateral are parallel. And the pair of angles marked with the red arc that doesn't include the tick mark, that pair of angles is an alternate interior pair with regard to the left and right sides of our quadrilateral. So those sides are parallel as well. And we've now proven that the opposite sides are parallel. So we've proven that this is a parallelogram. And we've also proven that if both pairs of opposite sides are congruent, a quadrilateral is a parallelogram. Now we're given a quadrilateral with a pair of congruent opposite sides, and that same pair of sides is parallel. We're not given any information about the other two opposite sides. We can draw that diagonal again. We have two congruent triangles by SAS because the top and the bottom were given as congruent. That's one pair of congruent sides. The shared side DB and the two angles which have to be congruent because they're alternate interior angles relative to the given parallel sides. And then we can mark the remaining pairs of corresponding parts, which consists of one pair of sides and two pairs of angles. And two of the angles that were corresponding parts are marked with the red arcs that don't include the tick marks. And once again, because those angles are congruent, that means that side DA and side CB are parallel because alternate interior angles give parallel lines. And since we've proven the other pair of sides parallel, we've proven that the whole thing is a parallelogram because one of the sides was given as parallel, and we were able to prove that the other pair of sides were also parallel. If a quadrilateral has one pair of opposite sides both congruent and parallel, it is a parallelogram. Now we're given a quadrilateral. We're not given any information about the sides, but we are given that the diagonals bisect each other. And then we see a pair of vertical angles, so they have to be congruent, and that gives us a pair of congruent triangles, AMB at the top and CMD at the bottom. Side, angle, side proves congruence of that pair of triangles. And then we have some corresponding parts. The angles marked with the red arcs are corresponding parts, and of course side AB is congruent to side DC, also by corresponding parts. And now to finish this proof, the pair of angles that were congruent that are marked in red are alternate interior angles relative to sides AB and DC. So those congruent angles prove that side AB and DC are parallel by alternate interior angles. And now we've proven that it's a parallelogram because we go back to the previous way that we showed to prove parallelograms. We have one pair of opposite sides, both congruent and parallel. And we now know that a quadrilateral is a parallelogram if the diagonals bisect each other. Now we're given a quadrilateral that has both pairs of opposite angles congruent. We're not given any information about the sides. Well, we can draw one of the diagonals, and the triangle sum theorem tells us that the sum of the measures of the angles of each triangle is 180 degrees. And then you can look and see that the angles of the two triangles form the four angles of the quadrilateral. The sum of the measures of the four angles of the quadrilateral must be 360 degrees because each triangle is 180 degrees. Let each red angle have a measure of x degrees and each green angle have a measure of y degrees. And we'll do a little algebra. Since all four angles add up to 360, we can write an equation. 2x plus 2y is equal to 360. Then we divide both sides by 2 and we get that x plus y is equal to 180. And of course that's the definition of supplementary. So each red angle is supplementary to each green angle. And so each pair of opposite sides is parallel because supplementary interior angles on the same side of a transversal give parallel lines. The quadrilateral, therefore, is a parallelogram. And we've just proven if the opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. And here's a summary of ways to prove a quadrilateral is a parallelogram. If both pairs of opposite sides of a quadrilateral are parallel, the quadrilateral is a parallelogram. And that, of course, is the converse of the definition of parallelogram. If both pairs of opposite sides are congruent, a quadrilateral is a parallelogram. If a quadrilateral has one pair of opposite sides both congruent and parallel, it is a parallelogram. A quadrilateral is a parallelogram if the diagonals bisect each other. And finally, if the opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram.